So for tensile testing, the issues to address for this lecture are stress and strain, what are they, and why are they used instead of load and deformation? Plastic behavior, when loads are small, how much deformation occurs, and what materials deform least. And plastic behavior, at what point does permanent deformation occur, and what materials are most resistant to permanent deformation? Okay. First off, we have elastic deformation. So elastic deformation means reversible. So that means that when we apply a load, like in this rubber band, if we apply a load, when we release that load, it returns to its original state, okay? This is a rubber band. It's not a metal, but metals also have a part of their deformation that is purely elastic, and it's during the low load section. So what's happening in that material is very interesting. We only have bonds that stretch. And so if you looked at a very small area, section of that at a high magnification, you would see that the planes are splitting apart, but and that force versus deflection is linear normally, okay? But and then when we unload it, they bounce back to the same state, okay? And that's called linear elastic. There is another class of materials that are nonlinear elastic. Those would be things like this rubber band that I showed you. And I can feel that this gets to a point here where it becomes very difficult to pull it any further. And that is the region here where it turns up dramatically. These behave differently because they are not a closed packed atomic structure. They are composed of long chains of carbon bonds. And so those chains are getting aligned in the direction of the force. And once they become fully aligned, then the force is increased dramatically because we're pulling on the carbon-carbon bonds that hold those chains together. Whereas for metals, it just follows a linear relation in the elastic region. So if I were to bend a paper clip, which I'm not sure if I have, here we go. This is a straight edge. With a metal, I can flex it and it's going to bounce back. And that is my elastic region for a metal. So if I were to take my ruler and apply even greater force to it, and I really don't want to ruin my ruler, so I'm not going to demonstrate what happens, but you get the point. If I bend this a lot, it's going to turn into a U shape. And I will still have that elastic bounce back even after I bend it into the plastic deformation. But I've also caused some sort of shearing of those planes of atoms. And so the plastic portion is permanent. You can't get that back. I mean, you can if you were to like turn it over and bend it in the opposite direction, perhaps. But you will still be able to get back that elastic part of it. So who can tell me the name of the point between the linear region and the nonlinear region?
Is it the yield stress?
The yield stress, right? Exactly. So this is the yield point, and I haven't talked about the stress yet, but yes, there is a yield stress there. So let's look at what engineering stress is. Engineering stress is just the force sub T, which is tensile, over the original cross-sectional area. And the original part is key to this term being called engineering stress. So if I were to look at the units for what stress are, since force can be either newtons or pounds, and area is inches squared or meters squared, then the units for stress are pounds per square inch or Newton per meter squared. What's another name for a Newton per meter squared?
Pascal.
Sorry?
Pascal.
Pascal, correct. And so from now on, we're going to be working with pascals, okay? Engineers, that's what we do, okay? We disregard a lot of the English system. So there is something called shear stress, which means that we're applying a force that is not perpendicular to the area of interest. And now we have two components of force. We have the tensile and shear. And by the way, this is mostly review for all of you. So I can just skip forward to the next one. The other one is called strain, and engineering strain is when you divide by the original length. Okay, that's engineering strain, and so it's the change in length over the original length, and this is epsilon. This is the strain, and it's a unitless dimension. Okay, but since volume is conserved, then if we have an increase in length, we're going to have a resultant decrease in the width as we pull on this. And so, who can tell me what that ratio is called that defines the amount of change in length relative to the amount of change in width of the sample?
Poisson's ratio.
Exactly. Good job. It's the Poisson's ratio. So that's another thing that you're going to be able to calculate from the data that's going to be provided. And the reason that's the reason why we put strain gauges on our tensile specimens in both the transverse direction and also in the parallel direction. Okay, so by just looking at the differences in those strain gauge readings, we can calculate Poisson's ratio. All right, so and there's your lateral strain. So there is a property of the material called modulus of elasticity. This is capital E. It's also known as Young's modulus. And this is the slope of the line of the stress strain in the linear elastic region. So if I have a material where the elastic modulus is quite large and one that is small, what would be different about those two materials? Why would one material have a very large elastic modulus while other materials would have a small elastic modulus? And it relates back to the earlier slides where I was showing you those atoms and what they were doing.
One material has stronger bonds.
Correct, or very close to correct. How strong the bonds is more of a relationship with the yield point, okay? Because the yield point is when those bonds are actually breaking. But what happens before the bonds are breaking? They're just stretching, right? And they're bouncing back. So that's called stiffness. So it's the I guess you wouldn't call it the strength, the ultimate, or the tensile strength, or the ultimate strength of those bonds. It's more of the strength of those bonds prior to that breaking point, and so we call that stiffness. If you were to take a spring, which is very stiff, it is going to require a lot more force to get the same amount of deflection. Okay, same with a a large rubber band or a smaller rubber band. So stiffness is a property of a material. So what would be a material that you know of that's very stiff?
Cast iron.
Cast iron? Yeah, cast iron. Pretty stiff. What else? What would be another one? It doesn't have to be a metal.
Wood is pretty stiff.
Carbon fiber.
Yeah. So one person said carbon fiber. I would definitely agree on the carbon fiber one. I have a carbon fiber paddle for my stand-up paddleboarding, which is very stiff, and I love the fact that it's really stiff. Some people might have carbon fiber tennis rackets, or you might even have a carbon fiber aircraft, if you're lucky. But wood, I guess it depends on the type of wood. But yeah, wood is possible that it can be pretty stiff, especially since you have all those fibers, and if they're in line with the flex direction. Good. So these all have very stiff bonds, and they all have very high elastic modulus. So, and that just kind of gets into this point here, where it really is a strong bonding or a weak bonding, not the ultimate strength of those bonds, but the stiffness of those bonds. Okay. And so the red line would be a very stiff material like carbon fiber, and the blue line would be one that has a low elastic modulus. So let's look at different types of materials and their Young's modulus values. Somebody mentioned carbon fiber, and then somebody mentioned wood, but this is wood perpendicular to the grain, right? So I don't even see wood on here parallel to the grain. Maybe it's pretty high. But yeah, I mean, you got diamond, which is the highest of Young's moduluses. And for the metals, it's tungsten. What do you notice about, like, within the metals? What do you see trending here from these metals to these ones down here? What other material property do you see in this trended data? What other material property other than stiffness or Young's modulus? You know, compare tungsten with tin.
Density?
Density.
Not entirely because of the gold.
Yeah, not entirely because you do have gold here as well. So maybe, maybe not. What else? You got nickel, right? That's certain types of aerospace applications use nickel. What type of aerospace applications use nickel? Inside an aircraft.
Batteries? Nickel cadmium batteries?
That wasn't what I was looking for, but yeah, sure, for sure. Yeah.
I don't know, maybe electroconductivity?
Let's see, electrical conductivity. Perhaps you got tungsten, probably very low electrical conductivity.
Point?
I'm sorry?
Melting point?
There you go. Who said that?
Me.
Me. Me. Who's me?
Ethan.
Ethan. Yeah. Yeah. Melting point. So, you know, when a material melts, the bonds break. And actually, when a material heats up, they start to vibrate a lot faster. And so that's related to the stiffness of those bonds, right? So the stiffer those bonds, the vibration isn't going to be quite as you know, good. And so you have tungsten, which is a great material for like filaments in those old light bulbs, because you could get glowing red hot in a very high temperature, and it wouldn't start to deform under that. Oh, and of course it wouldn't melt on you. Magnesium and tin, gold and all that, aluminum have very low melting temperatures. So, and what I was shooting for on the nickel was turbine blades. Turbine blades are primarily the main alloying element is nickel in those. And we all know why, why turbine blades have to have a high melting temperature and resist high temperatures, because that's where they operate. Cool. So any questions on this going forward? Yeah, yeah, carbon fiber, aramids, glass fibers. The glass fibers are, you know, made out of silicon dioxide. And within the glass fiber area, you have S-glass and E-glass. S-glass is the high strength of the glasses, and E-glass is lower strength. Okay, so plastic deformation we know is permanent. And going through a simple tension test, we see that the bonds are stretching, and they do return to the original point, and past a certain stress, we get the slipping of the planes, and that point is called the yield point. And we can reduce that load, and we're only left with plastic deformation because the elastic is reversible. All right, let me see if we got all right, so the yield strength, we've already touched on this, but there is a convention that we've all held to, which is noticeable plastic deformation occurring at a strain of 0.002. And the reason why we choose an offset there is because it's often difficult to determine exactly when we have a transition from linear to nonlinear. But if we take an offset and draw a line parallel to the linear region, maybe down here closer to the bottom where we can really identify that it's linear, and check the point that it intersects the stress strain diagram, that is now the yield strength. Now there's certain materials that have very distinct yield points. They actually go up and then they peak and then they quickly drop back down again. Those materials are very obvious where their yield points are. But materials like aluminum, which is what we're going to be testing with, we will have to do this offset. Okay, and that's what we're going to demonstrate in today's sample data. Does anyone have any confusion about the definition of yield strength? Okay, cool. So there's a couple of other material data points which we're going to pluck from our curves. One of them, let me get somebody back into the lab here. Somebody dropped out. I don't know who or what. One. Okay, so moving on, we have the tensile strength, which is the maximum stress in the engineering stress strain curve. Okay, so this is called TS, or tensile strength. Another point that we're going to pluck from our curves is the fracture ultimate strength, and that is when it finally snaps. So the maximum engineering stress strain occurs when we have noticeable necking, when the sample starts to neck down. And the neck is occurring because there is a localized weak point in the material itself. It might be a void, it might be an inclusion, something in there is causing it to finally found a weak chain in this connection of bonds, okay? And so the stress is going down, but that's only the engineering stress, because the engineering stress is divides by the original cross-sectional area. But in fact, the localized stress, which is also called the true stress, within that neck region continues to rise. So if I were to plot a true stress strain curve, it would keep rising and it would keep going up here. And if we could monitor the instantaneous cross-sectional area there, then we could plot the true stress there. But let's see. Yeah. Any questions on this? All right. So here is a table of materials and their various tensile strengths. the aluminum that that you are going to be looking at here. One of them is going to be a 6061, which is actually on this graph here. But we have two different types, 6061. One of them is just annealed, and the other one is aged. So wow, why would there be such a massive difference in tensile strength here between just annealing it and then waiting a while for some things to happen? Really dramatically increases in strength. Yeah. What's happening is we're giving time for very small precipitates. It's tiny ceramic particulates are naturally forming in the material. So it's becoming a bit of a composite, I guess you could say, to give it some extra strength on a nanoscale. These are very small ceramic particles, and these inhibit the movement of dislocations within the material. So you might be able to identify, based on the Young's modulus, which one is the 2000 series aluminum, which one is the 6000 series aluminum, and which one is the 1000 series aluminum. Those are the three different types of alloying aluminums you're going to see here. And based on the tensile strength, you might be able to determine if this is for the 6000, if this one happens to be aged, or is it just annealed. Okay.
I have a question about that.
Yes.
Does that change independently of stiffness, or is there an effect on the stiffness when it ages?
I would say no. It's not going to have any effect on the stiffness. And I'm pretty confident I can say that even without looking at the actual data, but you could confirm this by looking at the material property charts online. But those precipitates are inhibiting dislocation motion. And dislocation motion occurs beyond the yield point. And whereas stiffness is a property in the linear elastic region, which is only the area where we're stretching bonds. And so, precipitates aren't going to have any impact on the, stiffness of the bonds there.
Okay.
For the most part, yeah.
Professor Patton.
Yes.
How long would you expect to age aluminum to experience that kind of increase in tensile strength?
Not the simplest.
It starts to happen right away. And so the aging process is yeah, you know what, that's kind of beyond my knowledge, but I believe that if you have it annealed, then the aging process doesn't really kick in. Whereas if it's unannealed and just let it age, yeah. But anyway, that's something that I'd have to research.
Okay, thanks.
I think that'll be a big
Yeah. Good question though, man. I'd love to find the answer after this is all over. Okay. Any other questions on this stuff? Okay, perfect. Oh yeah, this is kind of cool. Carbon fibers. I always thought that the carbon fibers were stronger than e-glass and aramid fibers, but in fact, if you look at the the glass fiber reinforced composites is actually weaker. I'm sorry, stronger than the carbon fiber reinforced composites. The C stands for carbon, right? And that is really only the stiffness that you get an improvement in with carbon fiber. Okay. So what is tensile testing used for? All right, quiz question alert. Some things that it's used for is comparison of materials and their properties, alloy development, quality control, and to aid in the design process. So for quality control, you might pull a coupon from the aluminum furnace and machine a tensile test out of that aluminum, and doing that periodically, you can monitor the process, the quality control of that aluminum refining process, right? So for alloy development, you can test perhaps different compositions of silicon and magnesium and manganese and all these, and then check to see if you have higher strength or higher yield or whatever. And of course, to aid in the design process, perhaps you're doing a tensile test on an actual part. Then you can determine if it's strong according to the design that you've built for it. The stress strain testing is done in what's called these tensile testing machines. The one that we have here at Cal Poly is made by a manufacturer called Instron. It has a load cell up above, which measures the force. And I think it goes up to like 80 kilonewton for the one that we have. Then there is the moving crosshead, and this goes down and pulls on the material at a very slow rate. This is called a quasi-static test. So it requires a very slow pull rate because often materials are the strength can change depending on the plastic deformation rate, right? So as long as we keep it slow, then we can not have that additional factor being introduced. That's called strain rate dependency, by the way. And often we put an extensometer, and this is basically just like a little claw that attaches to the material, and it sort of like digs into the side of the material there, not digs in, but attaches there to where we can measure the extension. And there's other ways to do it, like strain gauges. And that's what we have in our lab. We put strain gauges on there to measure the strain. And then the third way is by just measuring the deflection of the moving crosshead. And the Instron has a very sensitive detector on the moving crosshead, and it also has a very bulky mechanical structure of the crosshead and the claws, so that you get very, very little deflection within the mechanics of the moving crosshead, and you can negate any deflection occurring in the crosshead with the total, amount of deflection. So all of the deflection is hopefully occurring just within your material itself. So those are your three methods: extensometers, strain gauges, and the deflection of your crosshead. So, okay. And a typical tensile specimen is round, and it always has a reduced section. But in our lab, we are using what's called DogBones. And DogBones are just sheet aluminum, which we CNC into a narrower section. I'm going to take a quick bio break, guys. Had too much coffee this morning, so just hang tight. Might be a good time for you all to go grab a coffee. Give me a couple minutes, okay? Okay, we'll give it another 60 seconds. We'll get another minute. We'll wait for folks to get back to their computers, and then we'll get started again. Okay. All right, guys, welcome back. Thanks for giving me that chance there. So these are called dog bones. This ensures that you have an increased stress concentration in the reduced section and decreases the possibility of failure at the grips, which you're going to be gripping. Your grips are going to go right in this region here. You're going to grip it here, and you're going to grip it right here. You just want to make absolutely sure that you don't have your grips like overlapping or intruding into the dog bone section like this. Not a good thing to do that. Okay. One thing that I have to research a little bit more is that I think the dog bones that we made were too thin. Were made out of a very thin aluminum, and that so it was only about 1 millimeter. That the dog bone wasn't narrow enough, and so the gauge length isn't just A. The gauge length extends all the way out to the grip, to the edges of the grips. That's not a good situation. That's not a very good test. So keep that in mind when you're analyzing the data, that if you were to have used a slightly larger gauge length, would your data coincide more accurately with your strain that you were getting from your strain gauge readings? Okay, so just a little heads up on that one as you're going through and analyzing your results. So the gauge length on these dog bones, I think, is like 57 millimeters. It's in the spreadsheet. Because we definitely had the wedge clamps attached outside of the dog bone region. Okay. There is a increased possibility of failure then in the reduced section, which is what we want. The wedges, the clamps, kind of dig into the aluminum, and if it were to have been just a straight material without any reduction in area, I can guarantee you that the break would be occurring right at the edge of the grips. And that's because we're creating a localized weak point where the claws are digging into the aluminum, and that is going to cause it to break there. And yeah, so. All right. So the testing conditions are defined in the ASTM, which stands for American Society of Testing Materials. Quiz alert on that one. And it's the standard for tensile testing. Now, there are many grip options. I've already shown you two. There was the wedge grips, which are what we use in the lab because we're dealing with sheet material. But wedge grips can also be used with wires. The other one that you saw was the threaded grips on the cylindrical specimens, which we do not use in our lab. And I said this before, the grip should cover any portion of the reduced section, including the fillet from the area where it's reduced. And each testing has a standard speed and temperature range, which is defined in that E8 spec. Okay, so in summary, you have stress and strain, which are size-dependent measurements of load and displacement, respectively. The key there is size independent because we are dividing it by the cross-sectional area for the stress or dividing it by the length for the strain. And by normalizing or making it size independent, now we can pluck the material properties from the stress strain diagram. We can get elastic modulus, yield strength, tensile strength, and ultimate strength from that. There's other things too that I didn't mention that we can get, like toughness, plasticity, and resilience are other material properties from mechanical testing, which brings up a really good idea that I just thought of, which next quarter I'm going to add the calculations for toughness and resilience and all that as well. So elastic behavior is reversible behavior, and it often shows a linear relationship between stress and strain. And to minimize deformation, you want to select a material that with a large elastic modulus. And that's because the slope of that region is greater. And in plastic behavior, this is permanent deformation, and it occurs when tensile compression reaches the yield point, which we define as with a 0.002 strain offset. Any questions?